Good afternoon and welcome to the Cabbage Lab pre-lab video. Now, here's our objective of our lab here is to determine the pH of various substances using a known color scale and identify which of the everyday substances, if any, could be potentially responsible for the damaged locker should charges be pressed against a student, maybe disorderly conduct or something like that. So, in this case, this is the objectives of this particular video, is to familiarize you with some of the chemistry background information needed to perform and understand the lab, but also to write your lab report if that's something that you're doing for this particular lab. I'll cover 4 topics in this video. 1, overview the pH system. 2, in order to determine an unknown, you must have a known to compare. How do we determine an unknown? Number 3, brief overview of how indicators work. Brief overview of our lab scenario. Important, this video is not a replacement for a reading lab procedure, so I'm intentionally not covering details of the lab procedure. It's a very simple lab procedure. Just read over the procedure provided in your lab book. Alright, so how does the pH system work? Well, first of all, the pH system is a measurement of things that make things that are acidic, for example, have H plus ions. We've talked about this, H3O plus ions. If we haven't talked about this, then there you go. This is the chemical that often causes things to be acidic. This can also be listed as an H plus ion. Okay, they're the same thing. They mean the same thing. So the more of this you have, then the more acidic you are. Okay. Well, if you want it to be basic, well, then the basic chemical is the hydroxide ion. And of course, the more of this you have, the more basic you are. These two guys, they don't like each other at all. They fight like cats and dogs, and they will annihilate each other. These guys do not like each other, and they will react in what's called a neutralization reaction. So, but in a sense, you should realize that the pH system, this battle back and forth here, is kind of like a teeter-totter. And H plus ions are on one side and hydroxide ions are on the other side. And as the H plus ions go up, the hydroxide ions go down. And if you have more H plus ions than hydroxide ions, it's greater, then we are acidic. But if for some reason you have more hydroxides on this side, right, than H plus ions, then you are basic. So it may sound strange, but every aqueous solution contains both hydroxide ions and H plus ions. Think about that. Both are present all the time. It's just a matter of who's in greater concentration. And so therefore, if they equal each other, then of course we would be neutral. So in a sense, you could track either the H plus ions that you see in this picture here, or you could track the hydroxide ions. So the pH system just happens to track the concentration of H plus ions. And the pH system happens to track the concentration of hydroxide ions. They really are kind of the same thing. They're mirror images of each other, and it's not a big deal, okay? It just so happens that H plus ions were involved in a lot of our food preservation systems, manufacturing, so they created the pH system simply as a way, because they're using it, whether it's canning food, making different types of foods, they used it. So they wanted a system that they could physically use, not just something to stick in a chemistry class. So because they used this one became more prevalent, but the pOH system could easily have been used as well. Okay, so let's sketch out the pH system and label where things are acidic and basic. Many of us are probably aware of this, that it's 0 to 7, and then 7 to 14 is our general pH system. The pH system actually is temperature dependent, and if you change the temperature, this is at 25 degrees, it will shift slightly. Either way, 0 to 7 is our acidic range, and from 7 to 14 is our basic range, and 7 generally is considered neutral. Our pH system would be just reverse of that. It would be 14 to 7 would be considered basic. Hold on a second here. All right, 14 to 7 would be considered acidic, and 7 to 0 would be considered basic. So these are both our basics. This is with the pOH scale, and this is with the pH scale. So we generally use this scale. If you measure the concentration of H plus ions, get the pH, which we'll eventually be doing, you can apply it to this scale. And just so you know, little thing that's coming up here, the pH system plus the pOH equals 14. So an equivalent P, like let's say you have a 4, the equivalent value on the other system would be 10. Okay? Or if you have, let's say, 5 on the pOH scale, which would be basic, would be equivalent, okay, to 9 on this scale, which of course was also basic. Okay? So just a different way of looking at it. Sometimes, again, if you're looking at a teeter-totter and you wanted to make a relationship to how high one side was off the ground, whether it's like this, or how high is this guy off the ground, or this one right here, do you need to measure both sides? And the answer is no. You could create a little algorithm to say if you know how high one side's off the ground, you would eventually be able to figure out how high the other side's off the ground. So it's kind of like that. All right, so that is a little brief overview to the pH system. Our next thing we're looking at here is going to be, in the real world, how do we determine, or scientists, medical professionals, determine unknowns? For example, how would they be able to test to know if you're pregnant? They have little home pregnancy tests. How do we know? How do you know if you have COVID or some sort of other disease? Even everything from cancer to other things. How do they know if you're on drugs? How would a drug test tell you're on drugs? How do they know if there's lead or some other chemical in your drinking water? So this is a major link that we're going to use to determine the identity or possible identity of some unknown. And this is something that has to be included in your lab write-up. This is a major link. Again, it's not necessarily the underlying chemistry. It's just a scientific comparison. And we're looking here is that in order to determine an unknown, I want to know what something is. Okay, in order to determine an unknown, you must have a known to compare. Okay, so this happens all the time. This is everything. If you, let's say, are a professional athlete and you are taking some sort of drug to help you perform better, you go and they test you for this thing, and they're testing against, they have a known value, so some sort of a known, they could take a urine sample, they could take a blood sample, and they have a known that says, okay, if they take the urine or blood and they test it, they run through this test, and it turns out like this, then this item's not present. If it turns out like this, then you have this thing in your blood. They're comparing it to known. Is it possible that you could take some drug that they aren't testing for? They don't have a known to compare against. Would they be able to find it? The answer is no, and this has happened in the last generation of people taking performance-enhancing drugs, and people have no idea that it's there because they're not testing for it. So either way, in order to determine a known, an unknown, you must have a known to compare to. So our lab is split up into pieces. First of all, we need to have a known, and we're going to create a known scale of what does it look like to be an acid? What does an acid look like? What's a neutral look like? What's a base look like? And we're going to create a known scale. And then we're going to test the unknowns. So what's known about our substance is the pH is known. So we'll have some known pHs. And then we're going to test some unknowns. What's unknown about the pH? You could say, for example, let's say baking soda. We're going to test baking soda. And sometimes someone might look at this and say, well, that's a known item. It's known. We know it's baking soda. But what's unknown about this is actually one of our unknowns. What's unknown about it? Okay, what the pH is the unknown. So you'll find our known items will have a known pH, a strong acid. Okay, this is from, let's say, 0 to 3 pH. We'll have a known weak or known neutral. Okay, so the neutral doesn't have a name, just this thing has a pH of 7. So when we're testing it against our known versus unknown, we can compare the known pHs to unknown pHs. So the things that have names on them that don't have pHs on them, those are our unknowns. Okay. All right. Again, with that information, you should easily be able to start thinking about how you would write out a conclusion. And this is some of the basic idea stuff we'll have in our lab report. Our lab report's not super complicated, but there's some stuff we want. All right. So what is an indicator? How does an indicator work? This is a chemical that changes color with pH or with changes of acidity. And it can go back and forth. So if you put something in an acid solution, it might turn one color, and then if you change it to a basic solution, it will change to a different color. So it could be, let's say, a common indicator in chemistry is called phenolphthalein. Okay, this is a real common chemistry indicator. In acids, it is clear, but in bases, it is pink. Okay, and it's not exactly. It's a pH. It switches over at a pH about 8.2. None of the indicators are great. Like, they're not absolutely perfect. Like right at 7 or right at whatever. There are lots of different indicators, and they change at all different types of ranges of pH. So, what makes a good indicator? One, it cannot be acidic. Cannot be acidic or basic. It can't do that. Needs to be neutral. So it doesn't want to play a part in determining whether it's acidic or basic. It just wants to be like a neutral observer. And something you might notice what makes a good indicator is how it changes, how the color changes. I would say that good indicators like phenolphthalein are slowly being replaced with, let's say, computers and sensors. But if you have a pool and you're looking to check the pH of your pool, then you're going to have a little color scale. You're going to dip a little strip into your water and you're going to compare it on a strip. That's using a chemical called a universal indicator, and it's another type of indicator that changes color with pH. So how it changes, and if it's a nice stark change, or how easy you can see the color, those are some things that make good indicators. Okay. Now we're using cabbage, which uses what's called an anthocyanin. So it's a very unique chemical, and again, this thing changes color. It's naturally located in lots of vegetables. And there are some plants. You can use rose petals, for example. There are lots of different things that change color with pH, naturally occurring things. Okay, so cabbage juice is not one of them. Now again, just because it changes color with pH doesn't mean it's going to be a really great indicator to be using in industry. Okay, so obviously cabbage juice is something nice for us here, but the stuff eventually it will rot. You can't eat it if you refrigerate it. So it's not something that is useful maybe in industry, but useful for us now. All right, so finally, what's our lab scenario? It appears that a solution has spilled in a student's locker and eaten which is dissolved or reacted to produce a sizable hole in the floor of the locker. This is something that very easily could happen. The spill occurred over a course of a few hours while the student was attending her gym class. The principal is looking to press charges against the student, making them pay for the object, this fix probably, for bringing a potentially dangerous substance into school. The student claims the substance was simply a household item, and therefore the incident is simply a large misunderstanding. So our job here is it does here mention that the lockers they're basically a steel product. Okay, the locker was old and some paint had been chipping away. Steel is an alloy of iron, and many reactions of both steel and iron are similar. So everywhere in our particular world, using steel, if you take a piece of steel, like whether it's a car or something else, we are always taking this steel and we're coating it, with coatings to keep iron from reacting from the outside world, and oxygen being one of the more important items. If you have a car and the paint starts chipping away, that's a spot where you can get a chemical reaction to occur where it wouldn't occur normally. Okay, so with that being said, this is kind of the scenario we have here. And we're going to see if this would work. So either way, that is the end of our pre-lab video. Again, you are stressed to read the very straightforward procedure. Thank you. Have a nice day.